All right, graphing polynomials, Algebra 2 Honors 4.1. So we are going to have you identify a polynomial function and graph polynomial functions using tables, and this is an important piece of end behavior. So first of all, we have just the general form of a polynomial, and I love this. It's kind of abstract with all the variables, but it's kind of neat. I'm going to use an example to try to help explain this a little bit. Say we have f of x is 8x to the 5th minus 7x to the 4th plus some stuff in the middle, and then say we have 3x and then plus 7. This a sub n and the exponent, the subscript on the a is just used for the coefficient. And it's kind of nice because if we look at this f of x here, because the exponent on the x is 5, we are going to say a sub 5 is 8. So the subscript just identifies the exponent that the x value is raised to. And it's just more convenient when you have high degree polynomials. When we just had quadratic, ax squared plus bx plus c, a, b, and c is fine. But what if you have x to the 8th as I have here? I don't want to figure out the letters of the alphabet to use as the corresponding coefficients. So we use the subscript to identify it. And then if we move to the second term, where the exponent is 4, then that means I would say a sub 4 is negative 7. So the subscript on the a, that a sub n minus 1, that just means that we are decreasing that power by 1 and that those are matching. So we're descending. And oops, I wanted to erase that. And so it's just kind of a cool way. So then when we get to this 3x to the 1st, that means a sub 1 is 3. And then the last term is what we call a naught. A subscript with a 0 is a naught. And so we'll say a naught is 7. And that is just your constant. All right, so a polynomial function is a monomial or a sum of monomials. So when I'm looking at this, each one of these is a monomial, and we are adding those together. So a polynomial is a monomial or a sum of monomials of this form. And we're going to say that when this is a sub n x to the nth, that the degree of this is n. And we always have that highest exponent first. And so therefore, I can't have a sub n equals 0, or it won't be of nth degree. So a sub n has to not equal 0. In other words, we have to have, if it's of degree 5, I've got to have a term with x to the 5th. And so a sub n is the leading coefficient, n is the degree, and a naught is the constant term. And the polynomial is in standard form when its terms are written in descending order of exponents from left to right. So we have a few different polynomials. We have constant, linear, quadratic we've been working with. And here notice they use the a sub 2, a sub 1, and a naught just to parallel that general form of a polynomial. Cubic is of degree 3, quartic is of degree 4. So those terms, constant, linear, quadratic, cubic, and quartic, you want to be familiar with. And so identifying polynomial functions. Decide if each function is a polynomial function. If so, write it in standard form and state its degree, type, and leading coefficient. So if we look at part A, we have an x cubed. There's no x squared term, but that's okay. 0x squared is fine. 5x and 8. It is a polynomial, and it is already in standard form, but it asks us to write it, so we're just going to copy it as is. And the degree is that exponent of that leading term, so the degree is 3. And it's of degree 3, so the type, go back to the chart, when it's of degree 3, it is cubic. And the leading coefficient, the a sub 3 in this case, is going to be -2. So there we have part A. Part B, we have an x cubed, an x to the 4th, and then we don't have a squared or an x to the 1st, but that's okay. But notice these are not in descending order, so it is a polynomial, but we need to put the x to the 4th term first, then x cubed, and there's no squared or to the 1st, and that's fine, it's still a polynomial. And the degree of this is 4. The type is quartic, and then the leading coefficient is √2. So you have to be careful and watch and make sure that they're in descending order. And then in part C, if I would rewrite that, x to -1, it's maybe been a while since you've worked with that, drops that to the denominator and makes it x to the 1st. And this being something other than an integer makes this not a polynomial. Not a polynomial. If we go back up here, the exponents have to all be whole numbers. And whole numbers are those 0, 1, 2, 3, 4, 5. You can't have -1, -2, -3, or rational. You can't have 2/3 or 3/5. Exponents have to be whole numbers. And so it defies the definition of a polynomial, so C is not a polynomial. And then part D, notice that we have this k of x is x squared plus 3 to the x. That exponent right there is not a whole number. And so anyway, this is not a polynomial. Example 2, evaluate this function when x is 4. And what that means is let x be 4 and plug that in. And so start by writing the original problem down. Show this substitution step. And 4 squared is, or 4 to the 4th is 4 squared times 4 squared, which is 16 times 16, so that's a 256. And 4 cubed is 64. And you end up with a -512 plus 384 minus 1. And that comes out to a -128 minus 1. And so the value is -129. So f of 4 is a -129. Show work. Notice the equal signs as I'm moving down. And you should have the original problem and show the substitution, not just an answer. All right, what's interesting coming up next and very important is end behavior. And so when the degree of the function is odd, and remember the degree is the exponent on the leading term. So on part A here, the degree of this first problem is 5. And since that is odd, it fits either one of these first two, meaning it's overall increasing or overall decreasing. One end goes up, one end goes down. And it's all according to then the sign of the leading coefficient. And the leading coefficient here is 8, and 8 is greater than 0, 8 is positive. So you have a leading coefficient that is positive, and the degree is odd. So what I know about this is that to the left it goes down and to the right it goes up. And then it can have some different turning points in between. Since it's of degree 5, there's actually could be up to 4 turning points. Not something that they actually ask you here, but something good to know. One less turning point than the degree. But I know since the degree is odd, leading coefficient is positive, I know end behavior is going down on the left and up on the right. And so how you describe it is in this way. And this is how I like to do it. So as x is going to negative infinity, then y goes to negative infinity. So as you're going to the left, y is going down. So as x is going to negative infinity, then y is going to negative infinity. And then as you go to the right, as x goes to positive infinity, then y is going up, so it's going to positive infinity. And so that is how you describe end behavior. All right, so then if we go to the next problem, part B, we will see that it is of odd degree, so it's either this one of these top two, but the leading coefficient, -4, is negative. So -4 is negative. And when it is of odd degree and the leading coefficient is negative, it's going to look like this in terms of end behavior. So I know overall, on the left side, it's going up, but on the right side, it is going down. It has to. And so how we describe it is we do as x goes to negative infinity first, as you go to the left, y is going up, so then y is going to positive infinity. As x goes to positive infinity, the function is going down, so then y is going to negative infinity. And that's how you describe end behavior. I put the x part first and the y part second, a little different than what the book has. All right, so then go to the next problem. And we have that it is of degree 4. And so the degree is even, so it's one of these bottom two. And so then we look at that leading term, and 5 is positive. So 5 is greater than 0, it is positive. And so it is following this graph where both ends are up. So when it's of even degree and the leading coefficient is positive, both ends are up. And so however this looks, the ends are both up. And so how we describe end behavior as x goes to negative infinity, then y is going to positive infinity. As x goes to positive infinity, then y is still going to positive infinity. Because when it's even degree and you have a positive leading coefficient, both ends go up. So then if we go to the next problem, we will see that it's of degree 2, so it is an even degree, so it's one of these two. And then that the leading coefficient, however, is negative, so it's going to follow this pattern where both ends are down. So negative 0.9 is less than 0, both ends are down. So however that happens, it's just of degree 2, so it's only going to have one turning point at the max. That's it. And so it opens down. And so we're going to say as x goes to negative infinity, then y goes to negative infinity. And as x goes to positive infinity, then y still goes to negative infinity because both ends are down. So there is your end behavior. Now, when you get to example 4, I want graphs, you are going to need to come back here and look at the directions. when your graph, include a table using values from -3 to 3, graph by integer, include end behavior, and be sure to identify the y-intercept. And so on this one, the y-intercept occurs when x is 0. So f of 0 is 0 cubed plus 0 squared minus 4 times 0 plus 2. So the y-intercept is 2. So that y-intercept is that point 0, 2. It is this constant. And so there's 1 point already on that graph. And then end behavior. Follow the example we had above. This is odd, so that means one end is up and one end is down. It has a positive leading coefficient. So I know on the left it goes down and on the right it goes up. Since it's of degree 3, it could have up to 2 turning points. And so my end behavior, and you have to actually list it, as x goes to negative infinity, then y goes to negative infinity. As x goes to positive infinity, then y goes to positive infinity. So you need to memorize that. So you need to list that end behavior. And that needs to be represented in the graph. As you go to the left, it goes down. As you go to the right, this goes up. And then do a chart of values from -3 and evaluate. And we're going to be looking at eventually here at synthetic division, but we don't have that yet. So now we just need to plug in -3, and you can do that on your own. So I'd already pre-done those. So if I plug those in, right, f of -3 means we are, plugging that -3 in and cubing. You need the parentheses just like that. A -3 and squaring, you need the parentheses just like that, -4 times the -3 and plus 2 and evaluating it. And so at -3 or at -4, plot the points. At -2, you are up at 6. And at -1, you're also at 6. 0, we're at 2, which we had already figured out. At 1, you're at 0. At 2, we are up at 6. And then at 3, we're at 26. So when this goes, you need to show that it's going off the chart between x values of 2 and 3. So now, because it has up to 2 turning points, and so I'm expecting maybe something like this, that means, from here it's going to go down, include an arrow, it's going to pass through, and since those are the same y, it's going to come up, hit a local maximum, come back down, and it's going to, if it's of degree 3, there can be 3 x-intercepts. And so here's 2, and so somewhere in between, it dips below and goes back up. And so how high it goes right here and how low it goes right here is, it can vary by student. That's okay. And so anyway, so there is a sketch of the graph. All right, so in part B, we want to find the y-intercept, which is going to be when x is 0. You get 0 minus 0 plus 0 minus 0 minus 3, which is -3. And so that y-intercept is -3. And then end behavior. Identify it. This is of even degree, but it's negative. So that tells me that both ends are down. And since it's of degree 4, you could have, up to 3 turning points. And so something like that. But the key is that both ends are down. So as x goes to -infinity, then y goes to -infinity. As x goes to positive infinity, then y still goes to -infinity because both ends are down. So then we just are going to do a t-chart. from using integers -3 to +3 and plug those in. Again, you're going to be putting in -3, so you need the opposite of a -3 to the 4th plus 2 times, oh, whoops, I got it ahead of myself here. Minus a -3 cubed plus 2 times a -3 squared minus the opposite of -3 minus 3. Kind of ran out of space there. And so anyways, and if you evaluate that, you will figure out that this is -36 and then do that value by value. I've already pre-done them. And so -3 is off the chart. At -2, we are at -1. At -1, we are at 0. At 0, we're at -3. At 1, we are at -4. At 2, we are at -21. So that's going to be way off the chart. And at 3, we're at -96. So on this one, it's a little harder to know exactly what's happening, but I know that it went off the chart. At -3, it's -36, which is way off the chart. So between -2 and -3, and then it's kind of arbitrary. We can have up to 3 turning points. So, and this one right here, we don't know exactly, but we're gonna just kind of twist it, go through, and have both ends down. And so as long as you have end behavior correct, you've got the integer values correct, the y-intercept, and it's a smooth continuous curve, you are going to be okay. So we're not using a graphing calculator, we're just kind of using general terms and some specific points, but end behavior needs to be correct, y-intercepts need to be correct, and you need to